Okay, let's start. Hi, everybody. So today the plan is to discuss um, about more advanced aspects of assembly programming. If you remember, in the last session, we have discussed about some important programming construct which are shared among pretty much all programming languages that you know, including assembly. Um, they were simple. So basically, we had maybe let's quickly review them. We had iterative construct, where we basically the task was to break down. Oh, come on. Where the task was to break down a step into multiple sequences. So this is called sequential construct. Very simple for any type of program. We essentially require these sequential constructs. The second one was conditional construct, where we check a condition, and this, that like it includes if, and essentially we will use this type of construct for also emulating for loop, while loop in assembly. And also iterative construct, essentially, that high-level languages such as C have these construct, for example, for while loop, but essentially in assembly, we emulate while and for loop, which is not integral part of language by checking a condition and in combination with a jump in order to emulate essentially an iterative construct. And we have a example. We went through it and we discussed it extensively how each of these constructs were used. This example, which was very very simple. Basically, counted the occurrences of a character in a file. So it was a useful example because it basically had the characteristic of interacting with input output of a computer. So it requires to calling a particular utility to interact with the operating system. But it had also all of the construct, including the sequential, conditional, and iterative. So it was a very simple, but at the same time, useful example to go through it. So I'm not going to go through it again. But if you have a question about this, please do ask now, so I can make it clear for you. But I hope it should be clear for you at this stage. And you remember we had particular utilities to interact with the operating system. We have the same thing in Mips through syscall, if you remember, and the machine encoding and how we can interpret it and how to essentially debug. And today the plan is to discuss about debugging, how we are going to debug an assembly program, and then discussing more examples, essentially high-level construct that we require, especially in Mips. And these examples would be very much helpful for also solving your homework. Hopefully you're making progress. I've seen some questions. At least some of you sent me privately. And if you have a particular question, please do ask it. I just noticed that Noah also sent me a question. Yes, you're right. So essentially, that's the second test case is wrong. Should be 0. I'm going to discuss it, but yeah. So I will essentially fix it and will announce it for everybody, so they know what. Hopefully, if they encountered the error when they wrote a correct program, so they know why that is the case. Thanks. Okay, debugging. As you know, so hopefully all of you have experience of writing in addition to debugging of high-level languages. For example, C, Java, or Python, or any other languages that you know. And debugging is a process of essentially tracing a program. And by tracing, it means that keeping track of a sequence of instruction and also checking the result that is produced by each instruction. And by checking the result, essentially meaning how the variables that you use throughout your program has been changed and how these variables are propagated, basically how the values of these variables are propagated through the execution of the program. And there are various ways of program debugging. Program testing is a large field, essentially in software engineering. So they have their own field. There are lots of tools out there for using, for debugging, for testing a program. But essentially, for assembly, including the assembly programs, even though we do not have very sophisticated testing and debugging tools out there for assembly, comparing with the high-level languages, but we do have some tools out there, and these tools, as opposed to high-level languages, that some of them are language agnostic. Here, they are very much architecture specific. The tools, for example, SPIM, you know, it's very much basically tied to Mips and so on. But essentially, debugging is, you can think about it as a technique that partitions the program into different modules. Although you can trace the program one instruction, one line at a time, but in order to be more efficient, you can think about the program as a set of more granular, more coarse-grained modules, and trace the program that way. So you can, instead of keeping track of each instruction, what happens, you can more efficiently break it down to more high-level construct or modules, and then proceed the debugging that way. You can think about this as a way for breaking down the complexity of a large program, right? So for example, if you have a program consists of several hundred, even 1,000 lines of code, it's very time consuming if you want to debug one line by line. You can find somehow you can localize the place or the location of a fault or bug more efficiently by basically breaking down into a high-level construct. You can think about it as a set, right? So what is the process of debugging? What is the goal of debugging is to find or localize where a fault or a bug is located. Okay, that's a goal we want to achieve. If you have a large program, is very difficult to find it line by line typically, unless it's very small. So if you want to search throughout a large program to localize something, it's better to break it down to different higher level modules. Is there any question? Let me check. Sure. Yeah, we can discuss about the homework. If you have a question, we can definitely discuss if that is helpful for you, or even I'm trying to finish, or at least to reach a good point today, and specifically the discussion that we have later on when we reach Mips should be also helpful for this homework, as I mentioned. Maybe we could figure out another session, maybe on Thursday, or even like over weekend, we could have some discussion, extra discussion about homework. If some of you are struggling, but I would like you to try, think, contemplate, and then we can definitely provide some help so you can make progress. Yeah, it's currently due tomorrow, but if many of you are struggling, I'm going to extend the due date. So hopefully you have more time to think, hopefully solve this problem independently, to gain some experience, again, to learn more, if that is helpful. I'm going to take a quick poll at the end of the class, see whether an extension is needed or not, but it seems that we need an extension. Okay, and there are, as I mentioned, there are tools out there for debugging. I'm sure you might have heard about like DBX, GDB, and other debuggers for C, for example, or Unix-like languages, essentially C, C++. Both of these are kind of Unix like kind of debuggers, and also some other debugging tools for other languages, but these are not applicable for assembly. For machine code debugging, we need some interactive debugging tools. And by interacting somehow, you already have a sense, or at least have some intuition, if you remember the way how a SPIM, how we can debug a program in a SPIM is to setting some breakpoints and like interacting with SPIM throughout the execution, and checking the values of each register and so on, in order to see what's going on. Specifically, we want to pin some specific values or enforce some specific values in memory and in registers in order to test the execution, at least of a part of the program in isolation. And isolating part of the program is essential part of debugging. And we can use different execution instruction by, for example, using run command. Run command, if you remember, execute until halt instruction or a breakpoint has reached, and a step n command execute a fixed number of n instruction. So let me remind you what I'm talking about. Maybe going back. Let me see. Okay. Okay. Screen. Do you see the terminal? Hopefully, it's the fonts are large enough for you to see. In a SPIM, we can use different commands to interact with the program, right? So first, we can load the program. Let's see. We can, for example, from these, maybe add to very simple program that we wrote together. Okay, we load the program, and you remember we can use run in order to execute the program. 26, right? If you remember, we have like two fixed number, and the result of this was 26 to a specific numbers, right? So you can use run to execute, but also you can use a step depending on how many lines of code that you have. Let me see. Check how many lines of code we wrote for this. So it was in total like 19. Let's say. By the way, you can use reinitialize to initialize, like to clear everything. So you can load the program from scratch. Okay, and then and one other useful command you may want to use is to get help if you forget a specific instruction, right? So you see the list of all commands that you can use interactively, right? So it explain what it means, a step, and step, like let's say 5. See, it executes 5 lines of code, and then essentially by this execution, the state of your program, state of the system has changed. And essentially by state means that like the number of the values assigned to each register that has been used has changed, and you can query to see whether these changes is essentially according to what you expected, right? So for example, you can do print, say. So we here, essentially, you remember, what did we do? So like, let's say, so this print all registers of the program. So you can check all the values and say, so far, it seems that we have changed a couple of, I mean, so far, it's just some reinitialization. We have not reached even main, right? So maybe we want to a step further. Let's say okay. Here you see we jump into the main. Main has started. We start by initializing the first register, the first value into a register. We basically wrote a program to add 7 to 19 and return the sum. So we use two different registers. So here, after we wrote to register number 16, it was S0. So we could use print to check whether the value that we wrote to a register matches what we expected or not, right? So in this case, yes, it is true. Yeah, very simple. But at any point after you execute a set of instruction, you can query the values of registers, and this is what you typically need. Registers, and also you can query a particular memory location. So if you see, you can also print a particular address in a memory. So you see if you dump a value of a register into memory, or you did some calculation in registers and then like wrote the result into memory, you can check whether these results make sense or not, or whether there is a bug somewhere happening or not. So basically, essentially these are the commands that you can use with SPIM in order to debug your program. And I highly encourage you to use this. Or one other command, which you already have discussed it, right? Breakpoint, and you know that this is the most probably useful command in order to debug a program. So you can set a breakpoint at a particular address, and then you use the step command in order to reach the particular address. Since from there you can continue maybe one instruction at a time in order to check whether the bug is happening after this particular set point. And you know the benefit of these set points. Set points are places in the program that you hypothesize most likely this is where the bug may happen, or roughly the area in the program that you think the bug may be located. So this is a useful thing to use in order to pass all of the previous instruction and start from where you think that the bug may has happened. Do you have any question about this? So hopefully this is clear. Yeah, and you can set a breakpoint, a stop execution, and a specific instruction, and examine what is in the memory and register in order to make progress. And again, to repeat that explicitly for you, memory and registers are the basically are the part of the state of the program, right? So you want to check these in order to find any potential bug. Let's have a quick example, very simple example. In this case, we want to multiply two numbers. So we want to multiply R4 and R5 in LC3. You remember we discussed like LC3 doesn't have multiplication instruction. So we somehow need to write a program to do multiplication for us. And this is how the program might look like in machine encoding. So we initialize these two registers, R4 and R5, to 10 and 3. And then the program produces 40, this program that you see down there, which is clearly a wrong answer. The answer to this should be 30, right? So we want to multiply 10 to 3. The result should be 30, not 40. The result that you get doesn't match the expectation, is not correct. Or to elaborate that, you might have a test case or multiple test case. As you have in your homework, the result that the program you wrote doesn't match the value of the value that is in the test case. So you get an error right away. Again, to elaborate on that, test cases are essentially a set of examples, and there you have some ground truth data which you already know that your program should produce these values, these correct values, when you run your program with this set of inputs, right? So these are, you can think about it as an explicit ground truth data to help you to test your code. Okay, let's see why that has happened. The first line, again, we initialize R2 to 0. R2, we use R2 in order to keep track of the calculation, or we want to put the result into R2 and return R2 eventually. So we then add, by the way, like one way of multiplying two numbers is to, for example, in this case, we have 10 and 3. You could add 10 3 times to itself, right? This is one way of calculating multiplication, very simple. So we first add R2 to itself. So basically we add R2 plus R4, sorry, we add R4 to itself one time, and then we change the value of R5. We reduce the value of R5 one time, meaning that we did this calculation one time, and we need to repeat that how many times? 3 times, okay? This is the logic of the program you want to write. So we reduce the value of R5 one, and then here we need to branch where we want to branch here. This is the loop that you want to emulate. So you need to branch to this memory location where you want to again do this calculation as many times as you need, in this case 3 times. So we use branch ZP, to remind you, ZP 0 or positive, and then we execute this until the program is halted, right? So if, in this case, if the value of R5, we reach this point when the value of R5 turns to negative. That's the only condition that we reach. We hit this, this instruction. And you already see, because it's very easy, right? Where the fault is, why the fault, why the bug has happened. Can anyone quickly remind others what is the bug here? It's very easy.
You asked for the problem?
Yes.
The problem is that it's running 4 times instead of 3 times. It's taking the 0 case. You don't branch. You should lower your registry. You forgot that it indexes from 0.
That's absolutely right, right? So here, at the first time that we hit this instruction, we put 10 to R2. So R2 is 10. Then R5 become 2. Then we branch, because R5 is 2, we branch. Next time we add 10, so it becomes 20. R5 turns to 1. Again, we branch. Again, we do this, becomes 30. R5 become 0. Again, we branch, because 0 and positive. We branch, and then R2 become 40, which should not happen. And the bug is becomes clear for you. This Z should not be there. So this should be branch only if the value of R5 is positive, right? If we change this instruction, so you saw what was the bug. If we change the this instruction, we use branch positive, basically changing this middle bit to 0, then the program work correctly. Is there any other way that we can change the program rather than, like, for example, say we want to use branch ZP. Is there any way to fix the bug, still be able to keep this instruction?
You can always have an instruction to subtract 1 from R5 before you start the program. Or you can have it branch on just positive and not 0 or positive.
Yeah, so yeah, branch only positive, yeah, works perfectly. We just like need to change this instruction. But what I'm asking, let's imagine we want to keep this branch 0 or positive. Is there any other changes that we can do in the program in order to fix the bug?
You could always set R2 to negative your R4 value at the beginning. That way you're adding 1 time extra, but you're starting with a negative number.
R2 to negative number. So you mean that we start R2 by instead of 0, negative number of what exactly?
Negative R4. So in this case, negative 10.
Yes, you could do that, but it's not very clean, right? Yeah, definitely you can start by negative number, but this is like, you don't want to do that, right? It's not really a clean program, right? But obviously it produces the right result. Is there any other way? Maybe you want to think about it. But essentially, there are, in many cases, and again, this really would go back to the trade-off when you write a program. There are different ways of writing a program, right? Some one way is like only considering performance. You want to write it in the way that produces the result in the fastest possible way. Some other way is you want to write a program to be as much as readable and maintainable as possible, right? And always there would be trade-off, even like for fixing a bug. You can fix it in a way that maybe it temporarily fixes the bug, but it would turn out to be producing another bug at some other places, or even turn the code into an unreadable code. So there are many different ways, or several different ways all the time, in order to change the code, in order to fix a particular bug. And it's always useful to think about it. This is the way how you can gain experience when changing changing the code. Essentially, this is related to the evolution of the code throughout the life cycle of the program you write. And this is true in assembly programming as well. Even though due to limited set of instructions or variability that we have in assembly, these variations are much less comparing to high-level programming languages, where you have like so many different instructions, so many different possibilities that you can change your program, simply because of the higher variability that you have in assembly. You still can change your program, still be correct in different ways, but these variability points are much less when you think about it and compare it with some other programming languages. So that's one thing that you may want to think about it. Okay, we discussed about it, right? So another useful way of doing debugging more efficiently is to think about corner cases, right? So when you have several variables involved in your program, considering corner cases, like for example, what if R5 is 0, whether you get the correct answer in this case or not, right? So in this case, if R5 is 0, you see that it still wouldn't produce the correct answer because it's already add R4 to itself at the beginning. So even if R5 is 0, like we add R4, so R2 become 10. If R5 were 0, so it becomes negative, okay? And then this wouldn't branch and we halt, and R2 is 10, while the value of R2 should, in this case, should be 0. 0 multiplying by R2 should be, by 10 should be 0. So these corner cases should be also a useful way of debugging the program, but you already have some idea of what I'm talking about. These corner cases are really problem specific. It depends on what kind of problem you're dealing with. And one way of designing test case is also putting some corner cases in your test case, in your test suite, in order to check that every time when you execute your program. Okay. Yep. Any question about debugging? Is there anything that I can make it clearer for you for debugging? Because you need to debug the code you write. Bobby, do you have a question? I'm not. You say that I'm having trouble seeing the R values stored in this in where. Yeah, if you could ask your question, that would be good. If I can help with that. Okay. Let's move on to Mips Assembly. More high-level construct that Eureka for writing more interesting assembly, Mips assembly programs. And let's start by if. If statements are one of those conditional construct that require for any code, most codes that we write. Here, the high-level code specify if two variables are equal, then we put the value of g plus h to f, and then we execute f minus I. Okay, so this is a if construct. This line of code, g plus h, only executed if I equal to j. This instruction, f minus I, executed when?
It executes regardless. It's outside of the if statement.
Is outside of if statement. Regardless, this line of code gets executed. So all the time. So no matter I is equal to j or 0, right? So this is not else part of if. I pay attention to these details in your exam or when you write code. This is the corresponding code in Mips assembly. Again, to remind all of us, here in the high-level code, if you see, we have several different variables. We have I, we have j, we have g, we have h, we have f. We have 5 different variables. And one of the important thing in order to translate your code into assembly is to decide what variables, what register you are going to use for each variable, right? So the assignment of the variables to registers is the first thing you want to decide. And this is what we have in the comment. And make sure that you put this assignment in as a comment in your code in order to make sure that you don't forget. You don't, especially when you want to debug your program, or if somebody else is looking at your code, they understand what's going on. Like you have like, even for 5 variables, which are not a lot, if you don't do that, like you will make mistake throughout the code. Okay. So here we assign f to S0, g to S1, h to S2, and I and j to S3 and S4. Okay. So One way of thinking, so you know that in Mips, we don't have like if construct, right? An if construct is a way of executing, of deciding whether we want to execute particular instruction if a condition is true, okay? Otherwise, we don't want to execute that, right? So is essentially is a kind of decision whether we want to branch after a set of instruction in the program or not. So if the condition met, we want to execute some instruction in the if part. If the condition doesn't meet, we want to skip that. Very simple. And we have this construct in Mips. We have something like branch, right? Branch not equal. We have different construct for branching in Mips. You already know that. But in this case, branch not equal, which is instruction checking two register values. In this case, we wanted to check I and J. We decided this register value to be S3 and S4. So we check the value of S3 and S4. We branch if these two values are not equal. Where do we want to branch? To a place which is labeled by L1, okay? So L1, again, is a label in Mips. You know that how to specify a label. And these labels, let me ask this question. What are these labels, right?
Functions.
Can you remind us what are these labels, essentially?
Go-to statements, basically.
Can you elaborate a little bit more?
Well, like so this is like branch not equal. So if they are equal, then you execute the command below B and E. If they aren't equal, then you go to that alias of L1, which is referring to that subline.
Okay, you're saying alias, right? What exactly alias mean in the machine at the machine level?
It's, I mean, I don't know if this would be right, but it could be like a reference to that command, because it might not be immediately above or below. Well, it isn't in this case. It's like somewhere else in the assembly code, and we need to jump to that essentially, is if I'm understanding correctly.
Yeah, you understand perfectly. So it's basically a memory location. And if you remember, like, again, I want to repeat that one of the fundamental properties of von Neumann model was that programs are stored in memory. So these instructions, this instruction, are in memory. L1 is alias or a label, and these are essentially the a memory location. One property that we have in assembly that we don't have in machine code is that this now we have this thing that we could use alias instead of, like in machine code we can't. We need to translate it into a specific location. This task of translating to a specific location will be done by assembler, right? This is the task of assembler to do that. So here we have this property that we could use. We could use labels to assign a particular location in the memory. So here we use L1, but could be anything. Again, these are aliases, right? So we branch not equal to if these two values are not equal, we branch to L1. What we have in L1 is subtracting S0 from S3, right? So what was S0? F, S3, I, right? F minus I, we put it to S0, which was F. Simple translation between this high level and assembly. And if these two are not equal, are equal, basically we don't branch, we execute the next instruction. Add S1 to S2, put it to S0. This particular instruction. And hopefully you know that no matter what, no matter whether we executed this command or not, whatever you have here, this instruction subtraction will be executed. So this translation is correct. Okay. So when even if you execute, if you don't branch here, after you execute this add, the program will execute this instruction afterward. Hopefully this is clear. So this is a way of implementing if statement in Mips assembly. So you have this instruction branch not equal or branch equal in order to write the code that you want to write. Okay, if else statement. If else statement is slightly different from the previous only if. In this case, the else part only get executed when the if part is not executed, or basically if the condition is not met. Slightly different than previous program. But quite similar, but here, like we want to have a way to also skip this instruction. We don't want to execute it no matter what. So we need to have a way, find a way in order to skip that part if when needed. Here is one way. Again, like this translation of variables to register values are very important. So here we use the same, we branch not equal to L1. L1 is here, but after we execute this command only get executed when basically this condition here, these two are equal together, right? So if S3 and S4 are equal, then this branch won't happen. We execute add instruction. Then we need to make sure once we execute add, we don't execute this subtraction. So we need to skip that part. How? Simple. We use jumped. We already know that we should not execute this L1. So we create another label. Let's call it done. We jump to this label and we continue afterward. Is that clear? So basically, it's a combination of two labels in order to simulate this if-else part. So it's not difficult, but slightly tricky if you are not that much familiar with assembly code. But at this point, hopefully you are. While loop. While loop is also another important command. Construct in a program. Here we want to determine the power of 2. Right. So we want to we have this this high-level code. What it does is basically initializes the power to 1 and x to 0, while this value of power is not equal to 128. It multiply power to 2, basically, and put it to itself, and then add 1 to x, and it does that. So basically, it calculates the power of 2 until this condition is met. Okay. So it's a very simple program, and eventually we are interested into having calculated value of x, right? So so at the end, like x should have the right value in order to return it, or use it in some other places in your program. So here, again, one way of translating into Mips. Again, this assignment of the variables, we only have 2 variables in this case, so we assign it to S1 and S0 and S1. And to remember, you can pretty much use any register in Mips to do this, but we discussed about like the convention of Mips. Typically, you want to use S registers or T registers, but any register should be available, and except 0, where you cannot change the value of 0. You can change any of the other registers. So here, we initialize S0. S0 was power. This is what it happens here. So again, for initialization in Mips, we typically want to use add-I. So add immediate, add 1 to 0 and put it to S0. And then here, if we initialize S1, the same here happening. Here, since we want to S0 in this case, which is the same, we could also use 0, but this is also one interesting way of like using add instead of add immediate, because 0 in this case is register, right? So you use you add the value of these 2 register, which is 0, and put it in S1. And then here, what we do is to use a temporary register T0 to to have this 128. So we assign 128 to T0. And then we use branch equal. And one way, typically this is most of the cases that happens, right? So when you have a condition, like for example, in a while loop, you need to like convert this condition because whether it is a, and this is true for if as well, right? So if you remember, and since like in again in Mips, we don't have like while or if condition, so we need to use branch. So one way of thinking about it is to convert this condition, negate this condition, right? So when we want to branch, when this is equal to 128. So we branch if T0 is equal to S0, meaning that if the power is equal to 128, where we want to branch it to done, right? To a place to continue, okay? So
do we need to multiply 128 by 4 to solve the byte addressing problem?
we need to multiply what value to 4?
Do we need to multiply 128 by 4 in the Mips assembly?
In this place, you mean?
Yeah, or is
Why do we need to do that?
to solve the byte addressing problem?
Not really. So we want to have a we want to assign T0 128, and in this case we use immediate, right? And here one thing to note that we are not loading an address. We are using this as an immediate value, right?
Okay.
So in this case, this is correct, right? I mean, I'm not sure exactly what you mean.
I'm referring to page 88 in the textbook. That's my bad. I just got a little confused. I was just trying to clarify.
Page number, yeah, maybe let's discuss it after the class. I'll stay around and point me to particular location in the textbook. We can discuss it. Okay.
All right.
Yeah, I need to look at it, what exactly you mean, but yeah, happy to discuss it. So we branch to done. Basically, we branch to like continue the rest of the program. If these are equal, if not, we want to multiply to 2. Here in binary number, shift left is used for multiplying to 2, right? So if you shift left a binary number, you essentially multiply that number to 2. Hopefully you know that. In previous courses, you already know that. So you shift 1 to multiply to 2, and you store it to S0. S0 again was this power, and then you add 1 to X. Here you use add immediate, and then you want to go back to the while. Here while again, this is a label. You jump to the while, so you execute it again until this condition is met, so you can jump to the done label. And one thing to note that even though like you could use pretty much any names, like you are not, again to clarify, you are not bind to use while here. You could use like a cryptic label. But this is a good practice to use meaningful labels, specifically when your code gets complicated. You remember like why you put these labels, right? So this would be helpful when you debug or you want to maintain your code afterward, or somebody else wants to read your code. Any question about this? So hopefully this construct is also very simple. Again, we translate while loop by a combination of branch equal and jump to emulate or translate that into Mips Assembly. And again, conditional branch and unconditional branch. We have also for loop, and the translation, like the difference between while and for hopefully is clear for you, specifically in C. So in for construct, you have some initialization, you have some internal variable, you initialize it, you have a condition, and you have an update to the for variable, and you execute this line of code until this condition are met. And here is again one way of translating is pretty much similar to while. Here we use add immediate in order to initialize some here, and then you use add to keep track of I. Is 0 to keep track of I. So we initialize S0. So this line is exactly what's happening here. Okay. And add I. So we add 10 to T0. T0 we use typically when you have a particular number as a part of the condition you are checking, you want to use one of these like temporary variable. You want to explicitly put it into a particular register, and the key reason is that the branch condition that you have is checking the value of 2 registers instead of 1 register with 1 immediate. It checks the value of 2 registers, branch equal. So and that's why you need to explicitly put this condition part into a register instead of like using this as an immediate value, because branch equal like expect to check the value of 2 registers, and that's why we need that. Okay. So here we branch if these 2 values S0, again, like this is negating this condition, like for this line gets executed until this condition is met, meaning that is I is not equal to 10. The negation of this is that if I is equal to 10. So if I is equal to 10, we jump to done. Otherwise, what we need to do is to add S1 to itself. S1 was the sum, and then use add immediate in order to increment I. And then we do this until we are done with this, and we can branch it here. So again, a combination of branch equal and jump, very similar to while. So if you compare it with the while, exactly the same, right? The only thing that has changed is like we changed label, and you know that you could use the same label. So essentially, is there's no difference in assembly between while the way how you have the you have the construct in Mips. There's no difference between while and for loop in some sense. Okay. Obviously, you have an explicit variable in order to increment. In some circumstances, maybe you don't have it in while, and this is what it distinguishes us of having having different construct in high-level language between for and while. Okay, so maybe let's, since we are past time, maybe let's stop here. I will continue the other construct that we have in Mips. Specifically, we're going to talk about arrays, which are important, and also function calls, which similarly are important. We had examples of this before, but making them explicit would be beneficial. So on Thursday, we'll have these, and hopefully we can write a program together. I will stay here a little bit. So if some of you have questions, do let me know. But otherwise, we are done. Thanks. Just give me a second. I'll come back and we can have discussion for questions answering. Okay. So who has question?
Professor, so the question I asked you on Piazza earlier had to do with the two test cases where we're using the longer half word and the word. I think they're cases 4 and 5, if I saw that right.
Right. Let me check. Sorry, I'm not sure why. Computer is so slow here. Not sure what's going on. Let me see. I think it's running out of memory or something. Just give me a second so I can check it out. Okay. So you're asking about the homework, right? So test case number.
The 4th and 5th cases where it has more than one and more than 2 arguments for the dot half.
Oh, these are like the same, right? These are basically, you can think about it having two arguments, but repeated multiple times, right? So repeated, like in the 4th repeated 3 times, the 5th repeated 5 times. So essentially, these are the same. Not very. Not really, not very different, right? Because your program, the program that you write, expect 2 values, right? These values are communicated through A0 and A1. This is how you communicate these 2 values. And if you look at the place where you jump into get bit in test case, let me share my screen so you can see.
I saw that it only runs get bit on the first half word in a TB_loop. So I'm assuming that that part breaks those longer expressions into those smaller half words that are 16.
Where are you referring to?
The beginning of TB_loop, the section you're in right now.
Yes. So we initialize 0 to A0, right? Yeah, here we retrieve the half word here into of the memory address. Is there anything incorrect here? Let me see. So when we run get bit, the values of So here you see that we load the address of bit vector start, which is here, right? So this is the data that we use, and you know that we can change this to any data essentially we want to check, right? Here we load the address of this into S0, and here we put this address into A0. Okay, this is how we needed to communicate with this procedure. So this is the address of the start of the bit vector. Okay. A1 is essentially what's happening here is we from these what we need to do is to communicate this number in each case, right? So 0, 4, 10, 16, 20, 21. Every time that we call get bit through A1, right? This is what's happening here. Load half loads the first number from this test data. This is again how we put the address of this test data here into A1, and here you know that we use S1 variable. I'm wanting to note here is that we need to, once we are done with each test case, we need to move on to the next test case, right? So essentially we need to increment or point to the next test case once we are done with one test case. So we need to increment that. This is what somewhere we need to increment, and this is what's happening here. Okay, so we need to increment the value of S1 and the way how you could interpret it, see here we use half word, right? So use half word for each of these numbers. So both numbers is one word, right? So next, in order to jump to the next one, we need to jump one word. We need to increment one word, and you know that one word is 4 bytes, and Mips is byte addressable. So that's why we increment S1. We add 4 to S1. So next time we jump to the next test case, right? And this is what it happens. Here is the same, right? So when we increment it by 4, then we are here, right? Next time here, right? So you could essentially, what you could do is also you could do this as well, right? It doesn't really matter. So you could change your test case in order to to put them in like one line or each two number in one line, or like stack them together in one line. This is the same way, right? You could split this into like this as well.
Okay, that makes a lot more sense. And so those parts right there, those long lines, are just for those parts of the bit vector start that use that those longer sections, or
exactly to somehow have a correspondence between these stuff that you have for longer sections, right? So we have right, one for each, right? And then we have like longer section here, longer here, right? Because we have 1 byte, okay? Here is the same, and then we have like this one, this guy.
that one's 4 bytes.
Yeah, so we use
No, it's 2 bytes. My bad.
yeah, so is 2 bytes, right? And here is a word, is 4 bytes, right? What I put? Yeah, I mean, like essentially this was, you could remove this. This would have been more clear, okay? Does it make sense?
Yes, it does.
Essentially, like some alignment between like these sections of your memory you want to check. But again, like it really doesn't matter. So this is somehow a more interpretable way of specifying your test cases, that your test cases become also more readable and more aligned to part of the test case, which is specifying a particular data, right? And you know that you can change this data, and like as a result, you also need to change this part, your test cases, but pretty much the same, right? The important part to get this procedure, this test case execution correct was to increment it properly, so each time we could point to the right part of the memory. But very good question. Thanks for asking it. And thanks for catching the bug. Yeah, that's right. This this is pointing to the second second half, and this should be, yes, this 0. That's absolutely right. Is there any other questions that I can answer?
So you said that we're not allowed to use pseudo instructions. So how do we know which ones are pseudo instructions? That
let me see. I think in I will, some of these documents that I shared should list the mapping, which one is pseudo, which one is not, to make sure that I point you into the right document. But definitely you can find it out into the comprehensive manual, but that's too long. In this quick reference, apparently it doesn't. Well, let me see whether I can find a quick reference so you can point to that quickly, and instead of going through the whole reference manual. That's also a good question. There was a question about part of the book. Who asked that? Do you want to ask a question?
Yeah, I was referring to when it's talking about loops in the on page 92 in chapter 2, and it says that before we can add I to the base array, save to the form address, we must multiply.
I can open the book so I can follow what you're saying.
All right.
My computer is too slow. I don't know why. Okay, page number
92.
92. Okay.
It says that you need to multiply the index I by 4 due to the byte addressing problem. And I thought that was for like every number. It must be just for like the base.
I don't see. So it is like Harris book, right? In page 92 is about like combinational logic designs, right?
Yeah, I got it mine from the bookstore, and they looked it up on the computer and gave me this book, but it looks like this. I don't know if this is the right one.
Oh no, this is like Hennessy. This is the Hennessy. That's also a good book. Okay, let me. So I have also that one. Let me open it up to check together. That's.
I told them I thought it was the wrong one, but they told me it was the right one. So.
I mean, like we don't use it, but also that's also fine. Is it the RISC edition or is the Mips edition?
It's the 5th edition.
5th edition. It's let me see.
I guess Mips edition.
Let's open it up. 22. Oh, okay. Oh, you're referring to basically the line which is labeled by loop, right?
Yeah.
So there it does shift left logical S3 two shift. Two shift means multiplying to 4, right?
Yeah.
So in our example, what we did, we multiplied by 2. So one shift is for multiplying by 2, two shift multiplying by 4, and 3 shift is this. This is essentially what happened. Let me explain it to you so you understand what exactly happening here. So you fully understand what's going on here. Okay, so when you have a binary number, like let's say you might have something like this 0, 1, 0, 1, 1, x 0. Let's say this is as an example. Okay, so what's this number represent? Like this is in binary, right? So convert it to decimal. What is this? Is
11.
Is 2021. So is 8 plus 2 plus 1. Okay, so it's equal to 13, right? Is that right?
I thought it was 11. Is it? It's not?
Sorry. Yes, you're right. You're absolutely right. So so when you want to multiply in binary, like when you every time you shift by left, meaning that you multiply it by 2, shift by 2, multiplying by 2 to the power of 2, multiplying by 4. 3 shift means basically 2 to the power of 3 multiplying by 8. And like you could see that why that is happening. So when you shift 2, this is what the result would look like, 0. So basically you shift everything to the left. So it would be 0, 0, 1, 1, 0, 1, 0. This is what you get. Okay. And if you want to convert that into decimal, it would be 2 to the power of 4 plus 2 to the power of 2 plus 2 to the power of 0. Okay. The result would be what?
Is it times 4? 44? Or?
Sorry, what is that?
I'm not sure off the top of my head. Just give me a second.
That gives you 22.
That's give 22, right? So essentially, you multiply this by 2. Okay. okay? So we shifted by left and we got the result multiplied by 2. And you could do the same, you could shift it twice, like this is what you get. 0, 1, 0, 1, 1, 0, 0, okay? So this would be 2, 5 plus 2, 3 plus 2, sorry, this one was 2, 1. In this case, sorry, this is 5, okay? In this case would be, should be 44, right?
Yeah.
So this is what's happening, right? So every time that you want to multiply a number like by 2, 4, etc., you could use shift. And if you want to the same, like for example, dividing a number, you could shift to the right. That's the way how you do it in binary.
Okay, so if you see a number in C code, are you required to multiply it by 4 in Mips? I don't know.
I'm not sure what you're saying. Not really. You should do the same, right? In the example that we have, let me bring up the example. The example we have is different from the book, right? In the example, we needed to multiply by 2, and we only shifted once to the left, okay? So here is the example. Here is our example, right? So we needed to multiply power to 2, okay? And here, why we shifted 1 to the left. The one in the book basically wants to multiply it to 4. It wants to multiply I to 4 and put it to T1, and that's why it shifts twice. Okay, it shifts 2 to the left. So that's different. Okay, does it make sense?
Yeah, that's better. Thank you.
Sure.
Are we still taking a poll for the homework? I know a lot of people are in chat asking if it's going to be extended.
Let me see. How many of you wants to? Yeah, it seems that like many of you are asking for extension. Yes, I'm going to extend it. Sure. Sure, I'm going to extend it. Don't worry about that. As long as it helps, definitely. Why not?
I also have a question about the homework, but it might seem a little like fundamental, but I'm just a little confused.
Yeah, absolutely. Happy to answer.
So like for problem 1, I get that we're trying to like check and see if the indexes of the binary number are equal to A1. But like, are we doing user input at all? Or no, do you give us like numbers to check it with automatically? Like, that's my first, like.
So you're asking, so if I understand it, no. So basically these test cases, like what you see in the data in the test data is going to, when you like complete your program, right, for problem 1, and you like fill out get bit, it's going to use your code, and it's going to execute it with different examples.
So we use our code from problem 1 and problem 2?
That's correct, right? So for problem 1, essentially you need to fill out get bit. For problem 2, so essentially problem 2 is a question related to the test case. But like both are referring to the same logic, right? So problem 1 is asking you to write this procedure to find out about a specific bit number, which could be either 0 or 1. And problem 2 is asking about the test case itself, which is test case is also a program itself. Okay. And you have the program already there, written there for you. So you don't need to write test case. You simply use the test case. But problem 2 is asking a specific question about the test case procedure itself. It's not asking to write it. Does it make sense?
Yes, more clear. And so do we need to loop through the indexes of the bit vector start?
It really depends how you want to write it. It depends how you think about implementing it, right? So and you can essentially implement it in different ways. You may need to use loop. Also, there are possible way of implementing it without any loop.
Okay.
And without any loop might be a little bit more tricky, but also more efficient. But I could also see a way of implementing it maybe with a loop. It really depends how you want to solve it. But there are few things that you need to consider, and we already have discussed about this, which is the byte addressability of Mips. Okay, this is important that Mips is byte addressable, and here the question is asking about a particular byte, right?
Yeah.
Okay. So this is important. Let me see whether there are some other important part. That you need to consider.
Would you recommend using SLT or like something more along the lines of branch if equal?
Either way is fine. I mean, SLT, you want to set a register and then check that register value, right? But you could also use branch equal if that also serves the purpose. These two-way could be equivalent if you want to use in your code. So one one way of thinking about it is to also the other point which for solving this problem is very important is to localize the right bit, right? So this is what you need to eventually turn, right? And the question is asking to it's giving you a specific bit number through A1, and you need to localize it first where this bit number is located, okay, in order to return the right value. And this is slightly a little bit tricky because this bit number is referring to any bit number in your
in the bitmap.
Right?
Are bit vectors and bitmaps the same thing?
Are what?
Is like in the homework it says bit vector. Is that the same thing as a bitmap?
Yes, they're the same, right?
All right, I was just clarifying.
Yep.
So how do we know which index to search for, like which bit number to retrieve?
This is given through A1, right? So A1 is referring to the bit number.
Like how do we know what to set A1 to?
Oh, okay, I got your question. You could assume that A1 has, when you start writing the code in GetBit, you could assume that A1 is already have the right number, right? Could be like any number, like in your vector, and these are already specified by the numbers that you see in the test data, right?
The test data in problem 2?
Yes, that's right. So maybe one way that could also help you is to try to trace the code in your test case, and essentially when you execute your code, it starts off by the coding test case. So tracing the code, maybe like even before you before you try to solve the problem, okay, maybe it would be helpful to understand what's going on in the test case, right? Try to trace it and like put a like, let's say, maybe put a dump code in getBit. Maybe try to print to the console whatever you have in A0 and A1, okay? You know how to do that, right? You can call syscall to print to console by setting the value of A0, like you need to communicate, when you want to print out something to the console, you need to put something into A0 and put a specific number to V0, okay? And then call it syscall. So you could do this, repeat this for both A0 and A1 to simply have like incorrect implementation, but just simply wants to print these two numbers, see whether these two numbers are communicated correctly to getBit or not. Like that's like the simplest way you can start trying to understand like what's going on. And then try to trace it one line by line, and then think whether, like I also put some comments at each line of code in the test scenario, like when it starts from the main, right? So at line 168, if you look at it, that's where the main starts. And when you run your code, you see that, like you could use a spin, you see that it starts there. Execute it line by line, and then see what's happening. What we discussed, you remember, we discussed today about like debugging. See what's going on, how these variables are changing, whether you understand each line of code in the test case, right? And if you have any question specifically about what's going on in test case, maybe you want to ask it in Piazza, ask from all others, right? So we can help you. But I'm sure you should be able to understand by looking at how the value of these registers are changing, and also looking at the comments, right? So I try to put like some self-explainable comments at each. This would be helpful to approach how you want to start writing your code for getBits. This is what I would suggest.
Okay, thank you.
Sure. Is there any other question that I can answer?
None from me, thank you.
Okay, sure. And if there is not, let me see whether anybody asked a question here. Yeah, I don't know whether these are like questions referring to me or not, but anyway, if you have any questions, hopefully ask it through Piazza, so others can also help. That would be good. So I'm going to extend the due date so you have more time to think about the question. Bye.